This is part 2 of lecture 8 of Elect 5300. We'll be talking about estimating the power spectral density of a random process. In this case, we'll move our discussion to a discrete time random process, and we'll assume that we have n samples of a discrete time random process, x of n. Now remember that the power spectral density is kind of like the average squared value of the Fourier, or squared magnitude of the Fourier transform. So one thing we could try to do is just take this set of data and just take its Fourier transform, take the squared magnitude, right, and then divide by n so that we get some kind of measure of average power per unit time, and say, well, maybe this is a good estimate of the power spectral density. We can take this one and just expand it out. This thing here is the squared magnitude, is just the thing inside here times its complex conjugate, right? And so if we assume that x is real, then we just get the complex conjugate by taking e to the minus j omega n here and e to the plus j omega m over here. We have to change the index of summation when we do the expand the product out. So now when we have the square term here, we get a double summation over xn times xm, e to the minus j omega n and plus e to the j omega m. So that's a minus minus here, which will give us the plus. And so then the question we have is, in what sense is the periodogram a good estimate? Now, this equation is a little bit complex, so in order to avoid clutter, I'm going to avoid writing the summation, the limits of summation here explicitly. So it should be understood that all of the limits of summation always go from 0 to n minus 1. We're always summing over those n data terms that we have. And of course what we can do is look at the same things that we were interested in before, the bias of the estimator and the variance. And remember what we want. We want the bias to be 0, and we want the variance to go to 0. Unfortunately, neither of those things is true in this case. However, one good thing that we can say is the periodogram is asymptotically unbiased. Right? So as we collect more and more data, the expected value of this estimate here eventually gets closer and closer to the thing that we're trying to estimate, which is the power spectral density. Now, to prove that, what we're going to do is we're just going to take the expected value of the periodogram estimate. We're going to substitute in the definition that we got on the previous page, which is this one here, and then do the same trick we did before, switch the order of integration, summation and expectations. We move the expected value inside here to cover the random variables here, and this is just the autocorrelation of x evaluated at the time shift n minus m. And this thing here looks almost like the Fourier transform, right? Except for the fact that the Fourier transform is just over one variable, right? Not two. And the Fourier transform goes over all time shifts, not just a limited number of time shifts. But to see what happens with this double summation, we expand the summation. We look at all the points in n and m, which this sum is taken over, right? And so remember, the sums all go from 0 to n minus 1, so we sum from m from 0 to n minus 1. We sum over n from 0 to n minus 1. And so the double sum goes over all these points in the 2D plane of little m and little n. Now, the thing inside that we're summing over here is constant along lines where n minus m is a constant. So n minus m is a constant along diagonal, or lines that are parallel to this diagonal here. So this diagonal here is where n equals m, or n minus m is equal to 0. This line here n minus m is equal to 1. For example, this one here, I've already written it. N minus m is equal to minus 2. And so, since it's constant along here, we can do the summation easily along this direction just by counting the number of points along this direction. Right? So we can rewrite the summation, the double summation, as by first summing along this direction and then summing along this direction over here. So when we sum along this direction, all we have to do is count the number of points, and we know that, well, when we're over here, and so we're going to call this time shift here, the direction along here, k. Right? So we're going to say, let's say this point here is n minus m is equal to k. We're going to sum from k is equal to minus n minus 1 all the way up to n minus 1. And so this summation here goes from minus n minus 1 all the way up to n minus 1. And so when we're at n minus 1, we only have 1 point. Right? So here n minus 1, n minus n minus 1 is just 1. All the way, and when we're at 0 here, when k is equal to 0, we have n points. So when k is equal to 0, we get n points, and then when we keep on going up to plus n minus 1, we again get 1 point over here. So this thing here is counting the number of points. This 1 over n comes from here, and now this is a summation over k, where k is equal to n minus m. And so when n goes to infinity, we can see two things happening. One is that the summation goes from minus infinity up to infinity, and then the term inside here, when n goes to infinity, this thing approaches 1. And so in that case, we would get that this thing is equal to the summation of k is equal to minus infinity to infinity of Rx of k e to the minus j omega k, right? Which is exactly the power, the Fourier transform of the autocorrelation, which is the power spectral density. Right? So this is true if n goes to infinity. So asymptotically, the expected value of our estimate gets close and closer to the thing that we're trying to estimate, and that's good. So that suggests that the more data we have, the better. We'd also like to have that the variance should go to 0 as n goes to infinity. Unfortunately, that is not the case. What we can show is, in fact, even in the case where x of n is Gaussian, which is usually the case we like to look at, because usually most of the good properties of the occur when the random variables are Gaussian. Even in this case here, we don't get that the variance goes to 0. In fact, there's a lower bound on the variance, which is the expected value of the thing of our estimate squared, right? And so remember, this expected value doesn't go to 0, right? The expected value here ideally should go to the, or in fact, we just proved that it does go to the thing that we're trying to estimate, the power spectral density, right? And so usually the power spectral density won't be 0, because if it was, it wouldn't be a very interesting process. So there's a lower bound on the variance, so the variance cannot go to 0 as n goes to infinity. So how can we prove that? Well, the first thing, we just say, well, the variance of this is just equal to the expected value of this thing squared minus the expected value of this quantity squared. Now I'm just going to look at this part here, because we've already looked at the expected value of in on the previous page. So we know that the expected value of in is given by this expression here. So we just have to get the expected value of in squared. So we substitute in the definition for in inside here. We get a double summation squared. So when we do that squaring, we get a quadruple summation, and then we can take the expected value and move it inside that quadruple summation, right? So the quadruple summation is over nm xn xm e to the minus j omega n minus m, and then we just repeat that for two new dummy variables of integration p and q. Right, so we get a quadruple summation, and now we've moved the expected value inside that quadruple summation here. And it turns out that for a Gaussian process, it can be shown that this fourth moment here can be expressed as some kind of product of the second order moments, or the autocorrelations. So this one is a special property of the Gaussian random process, and kind of you might expect something like that to be true because the Gaussian random process only depends on its first and second order moments. So the fourth order moment isn't going to give you any new information, and so you should be able to figure out what the fourth order moment is from the second order moments. And so in fact this equation tells you exactly how you can do that. So we're going to take this expression here and substitute it in for this fourth order moment. So here's the fourth order moment that we had before, and then when we substitute in the expression that we have here, we had 1, 2, 3 terms here, and so we're going to get 1, 2, 3 terms over here, and I'm going to separate the terms according to the values that are inside the autocorrelation. So in the first term here we had n minus m, and so I'm going to pull out the n minus m of here, p minus q, I'm going to get a p minus q over here, I get an n minus p in the second term here, so when I pull out the n and the p here, I get an n plus p actually over here, m minus q, I have an m plus q, and then when I have n minus q, right, I get an n minus q inside the exponential and m minus p. Right, so if I look at this one here and this one here, these two kind of all have a similar form, right, where this term inside the autocorrelation matches the term inside the exponential. Right, in fact we already showed that this is essentially equal to the expected value of the periodogram. So we showed this earlier, and so this is just the expected value of the periodogram squared. This is also the expected value of the periodogram squared, so we get these two terms here from the first and third terms, and then the second term here is just a little bit strange because we get the n minus p and the n plus p here, but we don't really have to worry about that so much, the exact form of this. The only thing I want you to notice about this one is that if the autocorrelation here is real, which we know it is, then this is really just the complex conjugate. These two are complex conjugates because they're identical except for the fact that I have a minus j omega here and I have a plus j omega here. So they're complex conjugates, so I have this thing times this complex conjugate, so that's just the squared magnitude of this thing here. Okay, so now what we're going to do is we're going to use this thing to compute what the variance is. Right. So the variance is given by this thing here. We computed this thing in the previous page, which was this. Remember we had these two expected value of in e to the j omega squared from the first and third term, and this was from that second term that we had. Now when we substitute this into this term here, one of these expected value of in e to the j omega squared disappears because it gets cancelled by this, and so we get the variance of this is equal to expected value of in e to the j omega squared plus something here. This is a squared magnitude, but it really doesn't matter because I'm just going to say this is always greater than or equal to 0 because it's a squared magnitude, and I'm going to replace this, I'm going to get rid of this and replace this equal sign by a greater than or equal sign here because this thing is always positive. And I know that this thing here does not go to 0. In fact, it turns out that this thing does go to 0, and the reason for that is here this is constant along the diagonals of n and p, but this is oscillating along kind of the the orthogonal diagonals, right? So if I just sketch that out quickly here, this is n minus p, is equal to 0, and this one here is n plus p is equal to 0. So this is constant along this line, and this is constant along this line. So this one is kind of oscillating in this direction where this one is constant. So this one is oscillating along this direction where Rx is constant. And so if I have an oscillation times a constant and I try to integrate over that whole thing, I'm going to get 0. So this thing is kind of going to go to 0. But this thing, unfortunately, will not. This thing goes to the power spectral density, which is generally not 0. So then the question is, well, how can we overcome that problem? Because that seems to be pretty bad. What that suggests is that as we collect more and more data, our estimate doesn't get any better. And so in order to address this thing, what we have to do is remember that what we did with the periodogram was that we just took our data and we just computed one periodogram. But remember, the power spectral density is really the average of the power spectral densities. The average of the squared magnitude of the Fourier transforms over the ensemble, right? But we haven't really done any averaging here to compute the estimate. So all we've done is just taken all the data and just computed one periodogram for that. And so instead of what we can do is we can try to compute k periodograms, right, from the endpoints just by taking the endpoints and dividing them into k different bins, and so we get m points inside each bin. And so now we can adjust. There's two free parameters here, m and k. K is the number of periodograms that we calculated, so we're going to average over the number of periodograms that we calculated. And each one of these then is an individual periodogram calculated over m points. Let's kind of illustrate that process over here. So suppose that we have 1024 points. One thing we could do is we could take all of these guys and we could put them into one periodogram, and we could take the Fourier transform of that. We get the Fourier transform at 1024 different frequencies, but you can see it's a very, very noisy estimate, right? Instead, what we could do is we could take those 1024 points, right, and divide them into k is equal to 4 bins, and each of those bins has m is equal to 256 points, right? Or we could take those 1024 points and divide them into k is equal to 16 windows, where each of them has 64 points. So like the periodogram, this averaging procedure still gives us an asymptotically unbiased estimate as the number of points we use to compute the periodogram m goes to infinity. Right? So to prove that, we just take the expected value of this thing, we substitute in the definition, and we move the expected value inside here. So we get the expected value of this. We know that this thing here is a periodogram of m points, right? And because of the fact that it's all coming from the same distribution here, the expected value for all values of little k are the same. So I can just look at the expected value of the first one and then multiply it by k. Then I divide by k so they cancel, so I get the expected value of the first periodogram. But I know that as m goes to infinity, this goes to the power spectral density. So that's good. At least that tells us that as we collect more and more data, we can make m bigger, and that will lead us to an asymptotically unbiased estimate. It turns out that the variance goes to 0 as k, the number of periodograms that we average over, goes to infinity. This should kind of make sense to you, because the number of periodograms, the more we average over the periodograms, the more we're kind of approximating that ensemble average. So why does the variance actually go to 0? Well, remember that when we only took the one Fourier transform of all the n points, right, then we actually got n frequencies, right? So when we take an n-point Fourier transform, we get n frequencies, right? And so therefore, if we use all n pieces of data to estimate only one periodogram, right, then we're actually estimating n parameters. We're trying to estimate the power spectral density at n different frequencies, right? And so as the data grows, right, if we only estimate one periodogram, we're actually estimating n different values, and so the data is growing as the number of values we're trying to estimate grows at the same time, and so the variance doesn't decrease. But the only reason the variance decreased before was that as the data grew, we were trying to only estimate a finite number of parameters, but here that's not the case, right? So on the other hand, if we estimate k periodograms, each with m points, and if we keep the number of parameters m constant, right, then the more data we collect, k, can be used to decrease the variance. So let's take a look at that in the example that we discussed before. Here we have all 1024 points being used to compute one periodogram. You can see that that's very noisy. The scale here goes from 0 to 7, right? Then when we divide it into 4 bins, right, what happens is that we only have to estimate 256 frequencies here. So this thing here was 1024 different frequencies, but now this is only 256 different frequencies. And so we can use those averaging by 4 to reduce the variance. And so here you can see this is still kind of noisy, but here the scale here is 4. Right? And if we further decrease the number of parameters we're trying to estimate down to 64, then we can actually get 16 windows in that 1024 pieces of data. So we only have 64 things that we're trying to estimate, but each point here can be estimated from 16 different estimates, and so the variance goes down. So you can see here it looks still noisy, but the scale here is only the full scale is only 1.4. So actually here this is much smaller. So 1.4 would only be, let's say a range from here, about here to here. So this little range here is that full range over here. Here's an approximate proof of why the variance goes to 0. So since each individual periodogram is based on a different set of data, we'll make the assumption that they're approximately uncorrelated. Right? So the variance of these guys here, of the average periodogram estimates, is just the variance of this, the variance of the sum. Again, I can move the variance inside here if they are approximately uncorrelated, but when I move the variance inside here, because it's a square statistic, I have to square this scaling factor, so I get a 1 over k squared of the variance of this. If these are approximately uncorrelated, I can move the variance inside here because the variance of the sum is the sum of the variances. All of these guys are the same. They approximately equal asymptotically as m goes to infinity. The power spectral density, which is a constant, and so this thing as k goes to infinity, this thing will go to 0. This is kind of an overly optimistic estimate because of the fact that, in fact, these windows here won't be uncorrelated, right? In particular, the values of the edges will be typically highly correlated depending on how quickly the random process changes. But anyways, that's a rough idea of what's happening here. Finally, I want to conclude with a discussion of k and m. So if I have a finite amount of data, let's say 1024, then the question is, well, how should I choose k and m? Right. But there's a trade-off here, right? Because typically what I want is I want m to be large, because if m is large, then I have a smaller bias, and I have an estimate of the power spectral density at many frequencies. On the other hand, if m gets large, right, then I can have fewer windows over which to average, right? But I want k to be large because then I get small variance. So here, with a finite amount of data, you can see there's kind of a trade-off between making m large or k large, and there's advantages to doing both of those, either in terms of bias versus variance. Okay, so that concludes our discussion of estimating the power spectral density, and what we'll do is move on and talk about Bayesian estimation in the next section.